Chapter 8.3 Quantities and Unit. Initially, we'll discuss the variety of forces: weight, normal reaction, friction, tension, thrust, buoyancy, air resistance. We'll discuss weight first. Weight is the force of gravity exerted on an object. It is important to know that the weight is not the mass. This is the earth. This is ozone layer, and this is the empty space. If we have 1 kilo of mass, uh, within this range, there is a force called gravitational gravity, and this object is pulled by that gravity towards the center of the earth. So then that is called weight. But in empty space, there is no gravity. So hence, there is no weight on in the empty space. The word weight is only applicable to the Earth or a planet where there is a gravitational force or pulling power towards a pulling power of object towards gravity. So empty space, just the mass, but there is no weight because there is no pulling power. How do we calculate a weight? We calculate weight by multiplying mass and the acceleration, or acceleration due to gravity. If I have a 10 kg mass, so what is the weight? The weight is 10 times the gravitational acceleration. Acceleration due to gravitation is 9.8, and this is kg, and this is going to be 10 times 9.8 kg meter square second per meter. So this is going to be 98, and this is we define as Newton earlier. Why this is? Why we have to multiply? Because according to the Newton law, F equal ma. This is a vector equation. We'll put down this direction. So m is 10 and a is 9.8 and 98 Newton. So this is the reason for this. We apply the Newton equation, F equal ma, to find the weight. So when this mass multiplied by the acceleration of gravity, that particular multiplication we call weight. This particular multiplication we call weight. There are two types of forces which occur as a result of contact between objects. One is normal reaction and other one is friction. To have both forces normal reaction, there should be two requirements. One, there should be two objects, and those two objects has to be contact each other. For example, if I keep this pen on the table, yes, two objects. So then there should be a normal force because one is pen, other one is then. So now there is no normal force. When I keep this one, yes, it's touch. Then there should be a normal force. Normal reaction is the force acts perpendicular to the surface when an object in contact with the surface. For example, if I keep this pen on the table and the normal is going to be, so this is the surface and the normal force is perpendicular to the table like this. If I draw this one, or will I'll draw differently. Assume this is the table. If I keep a ball on this table, what is the place where I contact? This is the place. From this place above, so this table will give a force to this ball from here. Usually we refer as R. So this is called normal force. If I keep, let's say, a box on this table, then we consider that like mass is everywhere it is touching is creating a normal reaction, but like mass acting on a one place. Likewise, instead of every normals, I can make one normal. Usually it's going through the center. Uh, why this is happening? Why this surface creating normal reaction opposed to these objects? Because these objects give a burden to the table. What is that burden? That burden is weight, W. And this one give a weight, W. As a result, we get this R. If you bring and if you don't touch this one, and if you hold basically, otherwise there is no way to keep, then you don't get R here, only W. The time you touch this one, you gave gave the object burden to the table, then it created opposite reaction. So that is normal reaction. This is for Earth. And if you keep this one in the empty space, now you have a table and you keep a ball here, right? So ball doesn't have a weight. So that touch doesn't make any reaction, normal reaction. To have a normal reaction, the object should give a burden to the other surface. That burden is weight. Sometimes it is part of weight. For example, this is uh, this is a wall. If you keep the ladder here and this is the floor, we know that this is a one object wall. This is the another object. We know this one touch. and it has a weight W, the ladder. So because of that, it create a normal reaction perpendicular. So this is action goes to perpendicular. And same as here, the flow, it create a perpendicular. This is R1, this is R2, it can't be same. Another example, assume this is a big ball and I keep a rod on it. So this is the place is touch, and now perpendicular to what? So this is a circle and you can see the touching point and the tangent line. So you can draw a tangent line, and fortunately tangent line is matched with the rod. So this is going to be perpendicular. So R is in this direction. And maybe weight is acting on here. The weight is acting on here in the middle. If it is a uniform rod. So this is the R. And now I'm going to delete this circle. Now what you can tell? Why this rod is not falling down? Because it has W weight and that W is covered up by R. Now I will clear this table here. So this is the unit actually we consider. We don't need table or we don't need this circle. So this is the unit we are going to consider. This is the unit we are going to consider. This is the unit we are going to consider. But if I really correctly mark this normal distribution, it's going to be something like this. So this is the ball, and now ball give a burden to this table. By applying a weight W, and as a result the table will give a reaction to it. We call from starting from here R, and according to the Newton law it has to be balanced. So then this is R. Usually we don't consider this one because we are not interested we are not interesting on table. So table is not the interested part of our sum. Only the ball, the equilibrium of ball, the motion of the ball. But if I make separately this one, we can see that this is ball and we have two forces. This is R and this is W, and this is R, and this is the table. So table I'll mark R here. For the table I'll mark R here. So this W actually belongs to this one, so I will write like this W, and this table give a R, upward R. So I will slightly mark from a side like this, and then that whole setup give a force to the table R. I know this is a bit confusing, but just for your knowledge, so just erase this one. And likewise, when you draw a table here, when we draw a table like this or ball like this, So it doesn't mean that there is another R here, but yes, there is a R here. There is another R here, but we are not interested because that object is uh, not the object we are working on. So we interest only on the rod. We only interest on this one, not the table. Another example, we can keep a particle on an inclined plane and the weight is down like this and the R is going like this. So then we only interest in this setup. In here the ball will come down, ball will fall up to here, then we have to do a calculation. Or sometime it can be a it can be a this kind of weight. Or another example, this is the table, or this is a particle or a mass, and this is a pulley, or this will go through the pulley, and at the end of the pulley there is a particle, another mass. So I'll write like this. So hence there is a tension. So now when you consider here, you have a weight here, and this object touch this surface, then as a result the normal reaction is here. We'll discuss a bit tricky one now. This is a scale. I keep a weight on this one. So now this weight is W. Give a burden, as a result it will give a R. Or I'll make, for you understand, I will write this R like this in a separate place, but I should go in the middle, and this is the table part. Now I'll bring another weight and I'll keep on this one now. So that is the weight of this one is W2. Now it create, because of this surface, this small cube will get another normal force like this. I will draw it separately again from here. So this is R, and now again one more, this R. So I will put this is R, then it can't be R this one, this has to be a different one. So I will put R1. Now if I draw separately, if I consider everything, only I have weight W, I'll put this in W1, W1 and W2. If I consider whole system, how many objects there? 1, 2, 3. Then whole system, the weight is W1 plus W2. If I put F equal MA to this direction, so whole system, then W plus W2, what will happen this one? So plus R1 minus R1 plus R, okay, I will put this is 2, So for the so this is 2 and this is 2 and this is 1 all. So plus r minus r plus r2 minus r2 because these are cancelling out when you consider whole system, and then the total mass uh, and maybe some other forces, or maybe this is attached to a scale like this t, and the t will come after that, minus t equal something like that. But if I consider separately, I'll consider separately this one. So this, then I have W2 here and then the R2 here. That's how it is. I consider this one. So on this one, W1 here and R1 here like this, and R2 here like this. And the scale now. For a scale, if it is a light scale, there is no weight. If it is a scale with the weight, there may be a weight, but only R1 there. If it is a light one, if we assume that this scale also has a weight, then we can make as a W3. So, so this is very important thing you need to know that. So when we consider separately, so how it's going to be look like. So this is a different color actually, but this is R2. So this R2 is this one. Then this W2 this one. This R2 is this, and this R1 is this one, and this is this one, and this one is go to the scale, because if we need to find R1, then we have to put F equal MA sometime only for this setup. And if I need to find R2, I might put to only this setup. But if you consider this weight and this weight only with the scale surface, okay, this one and this one only, then only you can see that W1 here, another occasion, W W2 here, W1 here, and this R1 here. So then you consider this both of object together. So why this is R1 R1 2? Because we know that every action has a equal and opposite reaction according to the Newton law. Now this is the normal reaction is as a result of contact. What will happen now? This is contact here, this pen. If I pull like this, contact and pulling two things. So that is where friction comes. In here they are fixed. We are not pulling each other. But if we pull like this, then normal reaction plus there is a friction is going to come. We'll discuss friction now. Friction is a forces which opposes the motion between rough surfaces. If the motion is in this direction, the friction is opposite to it, the other direction. For example, if you try to pull a mass, assume around 5 kilometer mass outside your house, attach into a rope, and you will see that when you apply pulling force gently, this will not move, and then you increase in your pulling power or pulling force, and after certain time it will start move. So the reason behind this scenario is friction. So in general, between two rough surfaces, uh, the friction is there. Without friction, we will never ever walk. So we need the friction to walk. And when we work in with sums, we have to be careful that about the surfaces given. Sometime they will tell that this is a smooth surface. Sometime in the sum it may mention rough surface. So if it's a smooth surface, and if this is a mass, and if we pull this mass, and so there will be no friction force. So no friction force if the surface is smooth. But if the surface is rough, then there is a friction force. So this is, let's say this is P, and so we have the mark like F. So this is the friction force opposed to the moving direction. So this is the moving direction. This is the direction having acceleration. Sometime when you work with sums, we can see that we keep the particle in a smooth plane. Then the weight, and now we know the normal reaction is there, that all, because plane is smooth. But if the plane is rough, then weight is here mg, mass times gravitational acceleration, and are also there, the normal reaction. Apart from that, the ball is moving in this direction. As a result, there is a friction force to this direction. Usually we mark this one, but friction is along this. The best place to mark is along this surface. Sometimes you can see this is a table, and this is a pulley, and mass is here, and another one is hanging like this. What the tension is there. Then we know that the weight is here mg, here also mg, weight is here mg, and the reaction for normal force is r. And if this given the plane is smooth, then there is no uh, friction here. But if plane is rough, then there is a friction here. We will mark like this, and let's name it as F. So that's how you want to mark the friction, because this system, when we release, sorry, I'll make it smaller. When we release, the system will uh, accelerate to this side downward. It means this is a smooth pulley and this mass will accelerate here. So this is the motion direction. And since this is a rough space, so we have to mark the F, friction. Later we will learn there's an important relationship between friction force and uh, normal force. That is, friction divided by normal force. So this is Fi referring to friction and R is the normal, and this is going to be a constant. Usually we refer this constant as mu. So then F equal mu R. By cross multiplying we can write F equal mu R. So this mu is constant and this is unique to the surface. For example, um, if it is let's say carpet, so sometimes there are rough carpet, rough, and this is another carpet. It is also rough. It is rough than this one. Then when we consider we are pulling the same uh, mass on both, this F divided by R, so it has a R. I will take R1 and this is F1 and this is R2 is different and this is F2 because the surface is different. So if this is F1 divided by R1 equal let's say mu1 and this is F2 divided by R2 equal mu2. This mu1 is not equal to mu1, mu2. If mu1 equal mu2 in any case, then the roughness of these two uh, surface are same. Assume for this surface I know mu value. So mu value is let's say 0.25. Then I can calculate friction force for this system considering this part. I can put F equal ma to downward, then I can see there is no acceleration on this direction. For this mass, it's moving perpendicular to that. So it mass is moving perpendicular to that. So acceleration is 0. Then so I put this direction. Then this one is positive. Mg is positive and R is negative because R is in opposite direction. So I consider this direction as positive, equal M times A is 0. Then we can see that Mg equal R. Now I found out R. Now I can write F equal mu R. So I know mu value is 0.25 and R I found out that is Mg, and I can find friction force if I have um, coefficient of friction in this surface. I know it is this day sometimes difficult to understand this one. Just leave it because we'll gradually will gain the knowledge, and you will be fine if you can understand this one. That's fine. And yes, friction. So sometimes we call that this is dry friction between two dry surfaces, and the fluid friction also there. If you do fluid mechanics in university or further, um, the fluid mechanics is there, fluid friction is there. There are a lot of variations of frictions, but in general, that's all. Now we'll discuss tension. Tension. When a string or rod is pulled, it will exert a tension force opposing the pull. Assume this is a string and two-person is pulling this string. So he is pulling to this direction. This person is pulling to this direction. Is pulled. It will, when those two people pull into those direction, opposite direction, it will exert a tension forces opposing the pull. Now, since this person is pulling this direction, the string creates string. It's difficult. So he is creating to this direction a force, and also this person is pulling to this direction, and as a result, the string create another force, the force to this direction. So this force is called tension. For example, assume instead of person, instead of a string, assume a person is there and two people is pulling those two person. What will happen? The person doesn't like this. Then person has to pull this direction, this person, and pull this direction to this person. As a result, this person will feel that he will be pulled by this person or a string, and this person will feel that he will be pulled by this string or this person. That's why the force we call tension is symbol in like this. Assume somebody is pulling a mass on the surface like this. So he is pulling to this direction, and because of that he will get a tension to this direction, and this one feel that this string is pulling him towards this direction. Basically, because of the friction force, this mass is not moving. So it's feel like this mass that pulling into this direction because of that friction. So as a result, the string is trying to pull this mass to this direction. In here, we refer here as a string or a rod. If they need to disregard the mass, then they will give it is a light string or light rod. We can see in our lessons that there are occasions that this is an inclined plane, and this is a mass, and this is a pulley, and this is attached to another uh, mass, and they will give this pulley is smooth. Then as a result we can mark this one, and this one is tension. Let me do it again. So this is two weights. Let's say and this is M1G, this is M2G, and this is a light string, and the pulley also smooth pulley. And now we can mark the tension. Now when you look at this picture, tension always, the arrow is going away from, that is the important bit. So basically when we consider whole system, the tension is disregarded. But if we consider this system, so in that case, this is the system. So you will see the tension is affecting away from this object, and this is the another system, the man with the part of a string. So that arrow is going away from this man. Likewise, uh, this arrow is going away, and this arrow is going away. And since this is a pulley, so we have to uh, use another two arrows like this. We have to break this. So we are sharing the tension from here to here and from here to here because there is a touch. Uh, the string is touched to this pulley. Since this is a smooth pulley, this T and this T same, and this T, the tension is the same everywhere. If this is a rough pulley, then this side is different and this side is different. Sometimes we may see a bead attached to a ceiling, a bead, a ring with a string. The string can move freely through the string, through the ring, and if this is a smooth, the ring is smooth and this is light, so that's how we mark the tension. For this direction, it's going away. For this direction, this is going away. And the feeling will feel that the feeling will pull by this tension. Since this is a smooth ring, so tension is equal. If it is not smooth ring, then we have to put T1 and T2, T2. But we don't usually deal with the in this stage with the string like that. Sometimes we can see this is a ceiling, a uniform bar is hanging on. Sometimes either with angle or without angle. So then this is a string, light string. This is also a light string, and the weight is here. And so this is going to be T1 and T1. So there is a tension because this is a string, and there is also a tension, but that is different to this one. That is not because of smooth, because it is a different distance, different attachment. So there are two systems when you consider here. One is bead and this one, and one is the other one is the ceiling. But we sometimes we consider everything together. Sometimes only the bead. So in this situation, it's going to be look like bead, and this is also same. This is one system. Other system is this one. If you accidentally mark the arrows like this, then it is an issue. So this is going to be a thrust. So we have to be careful when we mark, always closer to the object, away from the object. Next one is thrust. It is an object is being pushed along using a light rod, no weight. The force acting on the object is called thrust. This is a mass, and we try to push this mass using a light rod. And then what is the feeling of this rod? If the rod is a human being or has sense, what kind of feeling that rod will get? It is same like something I saw in a film that hero is inside, and this is two walls, and these two walls is coming closer and coming closer and coming closer and coming closer. Then what do you think that hero is going to do? He keep this hand is here, and he keep this hand is here, and he pushed. So the same feeling, so he managed to come out of like that as he's a hero. So the same feeling the rod get. So then let's try to push. The person he is creating is the, the force is creating to push this is called thrust, and usually we mark like this. Let me take this is P and this is P. For a tension it is going like this. This is for tension and this is for thrust. Person is trying to push, so as a result it make the thrust. Next we'll discuss air resistance. Air resistance is the force that is caused by air. The force is acting opposed to the moving direction. If we throw a ball to this direction and or opposite direction, the air resistance occur. The air resistance will slow down the motion of the object. If it is a ball is falling under the gravity, then the air resistance is upward. In a force diagram, we show it by a arrow, usually the F, and this is the mg. So F is the air resistance. So for this fall, we can put F equal mg to upward or downward. Let's say we put downwards. So then mg minus F, because this F is the opposite side, opposite direction, and m times the acceleration. Now this A is different from the J because it is under the effect of resistance, air resistance. If the ball go through water, then it's going to be water resistance, mg, and this is the water. So the water is blocking the motion towards downward motion. So then usually we call water resistance. And next one is buoyancy. Buoyancy is the upward force on a body that allows to float or rise when submerged in the liquid. So because of this, that's how the boats doesn't sink in the water because of this force. So this we also call buoyant force as well for this one. So this is mg, and usually mark with sometime with the bfb buoyancy. So the upward force exerted on the body. And finally, we will discuss the quantity and the symbols, units. The quantity and the units, so you already know just so mass is we measure by kilogram, length or displacement, the SI unit is meter, and the time measure with the second, and speed and the velocity. The distance divided by time. Uh, Distance divided by time. So distance measured by meter or displacement, and distance divided by time. So this is ms. This is going to be ms minus 1. And the displacement velocity means displacement divided by time. So again that is meter divided by s, ms minus 1. And acceleration is ms minus 2. So velocity divided by time. So velocity is ms minus 1 divided by, or we can write m divided by s, or m s square, or m uh, meter per square second. And the weight we measure by weight and force Newton. This is equal to kg ms minus 2. You can remember, if we equal ma, we take m equal 1 kg and a equal 1 ms minus 2, then 1 kg times 1 ms minus 2, 1 times 1 1 kg ms minus 2. This is 1 Newton. Let's discuss exercise 8c now.